Now let's talk about things that are warming up or cooling down according to the ambient temperature. That's the temperature in the air or maybe even water around them. So if there's a big difference between an object's temperature and the temperature of the air, then it loses or gains heat quickly, and if there's only a smaller difference, then it loses or gains heat more slowly. So Newton discovered, or I guess Newton gets the credit for it, I'm not sure who really discovered it, that the rate of change is proportional to the difference in the temperatures. Knowing what that constant of proportionality is depends on how much insulation there is and how much mass the object has and whether there's a wind or not. It's very complicated, so we're just going to kind of pick a number and see what happens. I have actually taken some data on this, and at the end of this slides file, I pasted in the data, and you can go see what that is later. So let's see our model set up. Let's do things minute by minute. Because we're in the US, we'll keep track of the temperature in degrees Fahrenheit instead of any rational system. Let's say the ambient temperature is 350 degrees Fahrenheit, and the object starts at 40 degrees Fahrenheit, and we said the rate of change is proportional to the difference in the ambient and object temperatures. We have to stop and say, why am I subtracting them in this order, or should I have a minus sign out here? So you can stop and think about, does this actually make sense, or we can just try it and see what happens. So you might be asking yourself, what starts at 40 degrees Fahrenheit in an ambient temperature of 350 degrees Fahrenheit? I'll give you a hint. I usually do this lecture, if it's a fall semester, right around Thanksgiving time. So let's go try it. We're going to be heating this object rather than cooling, but the math all works the same. So we don't need those anymore. So let's have this be our thermal transmission conductivity constant. And it's also related to thermal mass. If you want to know more about that, take a physics class. And we'll use 0.003 because I happen to know that works out well. And we'll use 350 as the ambient temperature in degrees Fahrenheit. And our delta formula has a little bit of a different form now. It's K times ambient minus object temperature. And that value is what we call K. We're doing this in 1 minute steps. And we said let's start it at 40 degrees, and our formula is the K value, molecular reference to that, minus times ambient molecular reference minus current object temperature. If the object's currently at 40 degrees and the ambient temperature is 350, should the temperature go up or down at the next time step? It's probably going to warm up. So I hope this delta formula gives us a positive number, and it did. Now this formula can stay the same. My new temperature is my old temperature plus the change in temperature. So I don't need to fill down anything there, but this formula I need to fill down. And I'm not taking enough time steps like I used to be, so let's go take some more time steps. That's probably enough. And what do we see happening here? Is that behaving exponentially? Well, exponentials can't curve that way. This one is trying to, but not doing a very good job. We ran it out for 300 minutes or so. Maybe we should try running it some more and see what it's going to do. Is it going to keep increasing forever? It's kind of hard to tell. We'll have to think about that. So take a sec to think about whether you think the temperature will keep increasing forever or what that means. Now, I'm kind of limited in the number of rows I have here. I'd have to go readjust my graph if I wanted to do more time steps. One way I can investigate the long-run behavior is to say, well, what if the thermal transmission just happens faster? Maybe I start a wind, or I take off in some sort of insulation blanket, or have a smaller thing so it heats up faster. So let me just double the thermal transfer coefficient here, and we'll see what happens. Let's try doubling it again. Is that temperature increasing forever? How would you describe that behavior? Let's make it even bigger. There's no particular reason I'm doubling here, it's just that doubling is fun. What seems to be happening to the long-run temperature there? Alright. So take a sec to think about how you would describe the long-run behavior there. Maybe pause the video and unpause it. Now let's really push the envelope here. Let's make this pretty big. How about 0.5? What do you think will happen? It should heat up pretty quickly, right? Seem to do that. Or if we make it even bigger, how about 0.9? How about even bigger? 1.5? It seems, let's do a zoom in here. If that thermal conductivity is too high, that actually predicts it'll heat up above the ambient temperature, and then back down below, and then above and below. Seems to be doing something interesting there. So maybe we should leave that here. We'll change the name here. Let's actually leave a copy of the strange behavior there. And here in the original heating and cooling tab, we'll go back to something more reasonable and run it out for longer. Did you figure out what starts at 400 degrees, at 40 degrees in a 350 degree environment and around Thanksgiving time? That's right, it's a tofurkey straight from the fridge at 40 degrees into the oven at 350.